Hi, Assalamualaikum. Today I want to continue the chapter FET DC biasing, which is chapter 2, with the topic P-channel FET. Previously, we have done three transistor, JFET, DMOSFET, and eMOSFET. All these three transistors are N channel, okay? So let's take a look. The P-channel JFET configuration has a different current direction. The symbol also different, okay? And then also the characteristic, okay? See, can we see that this is example of the circuit, okay? Common gate, because you see the gate is connected to the ground. Okay, and then the current is flow from S to D. Okay, and you see for the symbol now, okay, the symbol shows the arrow is pointing out, okay, from S to G. Okay, so this is P-channel JFET. So the characteristic will be opposite to the N-channel characteristic, where normally for the N-channel, the curve is at the negative side of the VGS. But now it become positive VGS. Okay. So we begin with the example 10. Okay. This is the voltage divider. Okay, voltage divider, and it use P-channel JFET. Okay, because you see the symbol, okay, the arrow is pointing out, and then the VP now is positive. Okay, that's a difference between N-channel and P-channel. So let's find IDQ, VGSQ, and VDS. Okay, first, what you must do is to draw the DC equivalent circuit. Okay, sometimes we have AC element in the circuit, such as the the input and output voltage, V in and V out, and we have also the capacitor. So remember that the capacitor will be open during DC analysis. That's why it will eliminate, okay, the V in and also V out that always connected at the D and for the output, and at the G for the input. Okay, after we draw the DC equivalent circuit, now we find the equation for the voltage divider bias. Okay, so the equation for the voltage divider bias is the VGS. Okay, so keep in mind that VG minus VS, right? So for the VTH, for the voltage divider, the VTH is equal to VG, and the formula is VDD multiply with R2, R1 plus R2. Okay. Then we calculate the VDD is negative 20 volt, and R2 is 20K. Then R1 is 68K plus 20K. So we get here 400, negative 400. And we get 4.545, or negative 4.55 volt. for the VG. And we find VTH, for the S now, VS. VS is, okay, let we see, okay, at the RS here, because now the current is flow from the ground, okay, to the D and to the supply. Okay, so the positive sign now is at the bottom. Okay, what can I say? That VS now is negative, because we have negative here, negative ID RS. Okay, it will flow opposite, okay, from the previous N channel that I have explained in previous video. Okay, so VS become negative ID RS. Therefore, the VGS is VG minus VS, negative 455 volt, okay, minus ID RS, become negative 455 volt. Okay, this one it become minus and with plus, become plus. RS is 1.8K ID VGS, or I can say VGS equal to 1.8K ID minus 4.55 volt. Yeah, so this is the equation for the VGS. Okay, now we go to the next equation, which is the Shockley equation, the second equation. So this is I mark as a equation number 1. Okay, for the Shockley equation, this we get the equation number 2. So we need to insert the VGS. Okay, insert VGS in equation 2. So it become ID equal 8 milli. 1 minus VGS is 1.8K ID minus 4.55 volt, can then divide by 4 and then square. Okay, and we calculate this one. So 1.8 divided by 4, we get 0.45 KID, and 4.55 divided by 4, it become 1.38, 1.14, because it's 38, right? So become n squared. Okay, so at milli, 1 minus 1.14, it plus, okay, 1 plus 1.14 minus 0.45K ID squared. So it become 2.14 minus 0.45 kilo ID squared, become 8.4 17. So we need to expand first this equation. 2.14, okay, 4.58, okay, 4.8 minus 1.92 93 K ID and plus okay, so 0.2 0 K squared ID squared, right? So 8 multiply 4.58 become 36.64 milli, and then 8 multiply 1.93 K become 15.44 ID and plus 8 multiply 0.2 K 1.6 K ID squared. This is equal to what ID. Then don't forget to bring the ID over here to make it the equation become 0. So here is 0. So we get 36.64 and then minus 16.44 ID and then plus 1.6K ID squared. So this is A and second one is B and this is C. Okay, now you can solve using your calculator or manually. Okay, this, let's recheck again. Okay, we check. Now we check. Okay, the equation B is 16.44. Okay, so it's correct, 16.44. And the A is 1.2K. 1.2K. Okay, now here I missing the 2K because I make it 0.2. It's okay, slightly different here, but it's still correct. And then for the C is 36.64 milli. Okay, so this is the calculation for the manual calculation. Then we get the ID1 and ID2. ID1 and ID2. Okay, then now it seems that both value for ID are acceptable. Okay, because both are more than is below the IDSS. IDSS is 8 milliampere. Okay, IDSS equal to 8 milliampere and the ID now is 8.84 and 3.31. So it is still in range with the IDSS. Now we calculate the VGS, okay, to check which current is acceptable. So again, we take this equation, insert the ID value. So for ID equal to 6.84 milliampere, the answer is VGS equal to 7.76. The second one, ID equal to 3.31 milliampere and VGS equal to 1.41 volt. And now you compare with the VP. Now VP for the N channel, for the P channel, VP is positive. Okay, VP is positive. So the given VP is 4. Okay, VGS 4. VP is 4. So VP equal to 4. Okay, it must be less than 4. So from these two, from the result above, the ID is 6.84. The VGS obtained has exceed the limit. Okay, you see, it has exceed the limit 7.76. So we ignore this one. So the value of ID equal to 3.31 milliampere. We will take this value, and this is the VGSQ. Okay, VGSQ and ID. This one is IDQ. Alright.